Hi everyone, welcome back to our YouTube channel, Becoming a ROS Developer. I'm Desire, and today I've got Matthew, who has just completed Python Basics for Robotics, and he will be giving us a presentation on that. So first of all, we'll see a demonstration on the real robot, and then we'll get into the nitty-gritties about how we managed to complete the task. So I'll hand over the floor to him so he can begin his presentation. Alright Matthew, whenever you're ready. It's moving pretty quickly. What velocities did you set for your linear and angular velocity? Mm-hmm. All right. So it started working better when you increased the speed. Maybe terminate and try moving it out, then run the script from a different place. Alright. Alright.
It was specifically to do something with the way I programmed some of the moving functions was not handling time and distance properly for moving backwards versus moving forwards, which I believe is a constraint of the distribution robot itself.
It seems to be doing the same thing as it was in the other corner. Oh, maybe disconnect and reconnect to the robot again. I hope it won't take that long, but we have to try. We might, yeah, I think we might as well try everything at this point, yeah. Okay, it's still doing the same thing. Okay. But can you move it with the joystick? Um, it's only when you okay.
I think part of what the problem is the little size of the
Uh-huh. Uh-huh. Okay.
See there, it's trying to figure out how to turn around such that it's not on
Mm. Yeah, okay, I think okay, so
apparently turning slowly. Once again, I think the problem with the corner is specifically at this size here.
it's not supposed to be doing that though. Okay, so
There it goes.
now it's moving.
Yeah, of course it just trips itself on the wall. And part of what's slowing it down, I think, is I added it so that when I try to move it goes backwards a little bit before it moves, just so that it wouldn't run into walls as often.
Okay.
Which heavily does slow down everything, but in simulation it ran into walls a lot less.
The other thing is what ranges of latest scan data are you taking into consideration when it encounters an obstacle? Yeah. As in, how many sectors are you splitting the front of the robot? Are you splitting it into 4 or like 3, 60, 60, 60 degrees? Or?
If I am not mistaken, I need to get into something there. Calculator, it should be it's left, and then front, which is technically broken into two pieces because it's measure in 360 degrees, with 0 degrees being directly in front of the robot.
Mm-hmm.
Front right and right, with front left and left terminating at 90 degrees from 0, so that's 270 and 90 degrees respectively, which actually I wonder if it would be for
All right, let's try everything in simulation to see how it goes, so we can. Yeah, let's do the class version and then the non-class version afterwards, just to see if they do the same thing, right? what did you say was the reason of having it backup? I thought 0.3 meters was good enough room to allow clearance on rotation, right?
Um, it was a personal design decision.
Okay.
It was also sometimes running into a problem where, for one reason or another, it would get too close to a wall, and then sensors wouldn't be able to pick up that the wall was there categorically.
Okay.
But if it backed up a little bit, then it was able to see, oh, right, there is a wall
Oh, okay. Okay. Yeah, clearly I see your logic here.
here with the antenna data stuff.
Mm-hmm.
If it gets too close to a wall, then you will break in that.
Okay. So it thinks there's
If it got
nothing.
too close, yeah, if it got too close to a wall, it assumed there wasn't a wall. So
Yeah.
I had to back up a little bit. It's like, oh, there's a wall there. Let me continue on like I should be with the knowledge that there is in fact a wall.
Yeah, but it's really taking a toll on how swiftly it runs. I like the fact that you took that into consideration, but on a performance basis, it's kind of affecting how quick it makes the decisions, which I guess it's not really a biggie on this one, but I think in future maybe you could make it slightly better.
Yeah. Something that I need to mess around with that could be seen as a conceivable alternative is to increase the range at which it detects walls.
Mm.
And say, okay, the threshold is higher,
Mm-hmm.
meaning it stays away from
Were you still using Were you still using the 0.3 threshold on this one?
less than yes.
Okay, all right. If you make it any bigger, do you think that would help? Because if you take the top right corner, right, it avoided it pretty nicely, right? It didn't get as close to the wall as we thought it would. But on this one, we can see that it's really getting too close to the wall. So I don't think it's a threshold thing. I don't know. You would have to like play around with your code a little bit more, but. But all right, so okay, this one is the class version, right? Let's do the non-class version. So.
So the non-class version, or the instructions, was basically you're like, oh, you write all functions and you basically test them
Mm-hmm.
just to be sure they work.
Just a side comment as we go. I think you can see that your methodology, right, to back up a little bit before making an obstacle avoidance action works better in simulation, but on the real robot it kind of struggles a little.
Yeah.
I think you're also supposed to kind of, well, this is me just speaking to thinking about the differences between what happens in reality and what is happening in simulation right now, right?
I think another thing that was really causing me about this struggle was the fact that the size of the struggle cases got
Oh, those ones. Okay, okay. So
because this code, as I understand it, only knows how to handle like square corners.
right, yeah, I see.
And measuring those distances gets really weird if there's certain objects in
Uh,
there, I would imagine.
Right, yeah,
I hypothesize that that is what was causing unusual behavior in simulation.
yeah, yeah.
In real life,
I'm inclined to
whereas
agree with you. Yeah,
when I manually pointed the robot at a wall, it was like, oh, there's a wall here, let me turn.
it
And
worked
it
better.
behaved like it did in simulation.
Okay, okay, I see. Okay, you can run this one and let's see.
So I know class, I used it to test all the improvement functions, as I did some of them distance-based, some of them time-based.
Mm.
If you just generic, like, okay, move a technically arbitrary distance that I chose.
Mm. So when you say distance based, how did you measure the distance? Can you just elaborate?
So distance is speed and time. So what I did is in all of my functions, I have it move at a certain speed per second per seconds.
Right.
What I did was I had it move at 1 space per second,
Okay.
and simply sleep for the amount of distance in seconds that the user passed in.
All right. I thought that would be a time-based one. Okay. So how does it differ from the time-based one?
The time-based one is that it moves at a
Okay, okay, so okay, it's dependent on the parameter which you pass as a regulatory measure. Okay,
Yes,
I see,
yes.
I see.
And now, since it stopped moving, I'll unpig this a little bit so you can see better.
Mm-hmm.
This is printing all of the data sensors have access to real time. So it knows, excuse me, the range from all the sensors. It puts its distance and angle associated with it.
Mm-hmm.
Angular velocities, linear acceleration, all of my odometry data, and laser speed.
All right.
Because it's just gonna constantly print it every 5 seconds.
Okay, okay.
Just playing around with this in a way that I can really control the robot, just to be sure all the sensors are reading correctly.
Okay. All right. All right. I think right now with the time that we've got, let's get a look at your code. Right. You can get into as much detail as you would like, because I think we've got enough time for that, and that's the most important part, right?
Great. So my routine is just to run with this pod. This is where all of the ROS magic happens. I import that in last and not last files.
Mm-hmm.
Starting out, I have all of my movement functions, so getting velocities, stopping, in front, left, right, doing all of those timed, doing all of those for distance or angle, respectively.
Mm-hmm.
Just getting the data, scan data, and index, which is actually right there. Front, back, right, left, standards. I just all get scanned with index.
Mm-hmm.
Static index of 0, 1, 2, 9, respectively.
Mm-hmm. So, you say this was very helpful. This method was very helpful. Can you explain to me in more detail in what way, in comparison to the other method? Because I'm presuming that you were thinking about other methods of doing it, and you realized this was very much easier.
It was the first thing that came to my mind to do. It was the most elegant, in my opinion.
Mm.
And the ability to say, okay, at any given angle, at any given time,
Mm-hmm.
tell me what the closest thing is,
Mm-hmm.
or like tell me how far away you think something is in that direction, was very useful for actually building the ranges at which the robot looks at things. Without this capability to do it based on index, I would have to find some other way to slice all the data that is used in the error scanner, and I'm not sure how I would do that if it wasn't for this tool.
Mm-hmm. Okay, I understand. Yeah. Okay.
There's a couple functions that max and min ranges not equal to infinity,
Mm-hmm.
which are also somewhat helpful, depending on the situation. Here we have geometry data, which is return as a list. Wheel pitch and yaw, which is also return as a list. Here we have the distance formula, which I use to calculate the distance the robot has traveled.
Mm-hmm. What was your um your origin?
So I pass in an x1, y1, an x2, and y2. Later on, I can get to how I determine x1 and y1 as part of origin.
Okay.
But
Okay. So this is like it's almost like origin independent. You just make whichever point you want the
yes,
origin, and
yes,
then
it starts wherever the user wants it to and
right.
ends kind of wherever the user wants it to.
Okay. Okay. Right.
Yeah. So angular velocity also returns a list. Acceleration the same. Then we get into actual micro. So given that this is the non-fast version, I
Mm-hmm.
have to go to testing static move, time-based move, and distance/angle-based move, just to see, okay, these things line up how they should.
Mm-hmm. So
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 if you,
on those two, which one did you find to be the most effective, or which one did you like, given the way it works, right? Because obviously they give you the same kind of output, but Which one worked best for you?
I found distance to be the most useful, as static was like, okay, it might read that it needs to go closer to the wall, but it doesn't know how much.
Okay.
Since the step size is static, it sometimes will run into the wall and keep moving for a couple seconds.
Right. Okay. Okay.
Kind of same with time. I guess for time, if I used got around this, given that we got sleep, it's
Right. Right. Yeah. So you also got that restriction. Yeah, I see. I see.
for distance, however, I can pass in floats.
And it doesn't worry you. Okay, I see.
Allows me to pass in very small units, so that it is constantly, it'll lose a tiny bit and then checks,
Mm-hmm.
which was where I found to get it from being thinking, oh, the wall is 0.45 meters away, let me move 6 meters
Mm-hmm.
forward,
Mm.
running the wall higher speed for a second, and then it's like,
Yeah. Yeah. Right. Right. Yeah. Well explained. Yes.
next is a tool section, also titled Tools. This is where I have it print out all of the data that's extracted.
Yeah.
One thing I do right at the start is I set an initial position variable, which extracts the current XYZ odometry data,
Mm-hmm.
which I then use for position. I pass that data into loading distance here, along with the robot's current position in the X, meaning this is accomplishing the task of determining distance from where the robot started to where it currently is.
Okay. So okay, I
But
see.
in a very abstract way, such that if you wanted to determine distance between any two arbitrary points, you could do so easily. It's not that hard.
Right. Okay. So this one just defaults to where it starts running, and the other one allows it to float around. You can pick where to start, where to end.
Yes.
Okay. All right.
Finally, this is laser scan data. This is that sleep I put in, so that after that time you look at the information and you're like, hey, that's wrong. Why was that wrong?
Uh-huh. Yeah.
As opposed to the terminals blowing up, because if I didn't let enough sleep there, it would be running constantly.
Right. Yeah. Yeah. That was quite smart as well. Yeah. Otherwise, it would be very difficult to debug. Yeah.
That's all the way to the non-class version.
All right.
Moving into my class version, I have basically all the same imports as before.
Yep.
Things. I define a robot control class. I set self.robot interface to be robot skin, which when I create an object robot control type, or instantiate, I pass it robot interface. This one, that's how it talks to the robot interface Python file where all the ROS
Mm. Okay.
I set all this data to be 0 right at the start, just starting the slate. I have data floating around in the completion thing was given to me. I didn't touch it. Now we get into movement functions. These are very similar. Here I am in velocities, linear and angular. Let's return. Stop, move from, move back, move left, move right. All of those functions are timed. All of those functions are related to distance and angle. Laser scanning functions. Speed X1 is going to do front, back, left, right. Scan, and then front left, and front left.
All right. All right.
Giving values, useful. Here's my odometry data. This is basically the same as non-class, except if I'm uploaded to use self-interface control
Yep.
in front of the robot. And first normalizes infinity values, extracts them manually. If minimum is greater than the threshold, then I run some stat stuff on it. If length is greater, then I'm pretty sure I want that the robot is looking up. If not, I'm pretty sure the robot is looking below.
Okay.
This is something they laid out the instructions here, given like, hey, just do it like this. It's the easiest thing.
All right. All right. All right.
This enable helper function is used a fair bit in tracking direction. So for direction, my sector size is 45 degrees. Since the robot sometimes results in greater than 60, I need to normalize the angle instead to 2.
All right. All right. I think we're running out of time a little bit, but yeah, it's all right.
I do logic to determine the ROS spacing, return that. Using my favorite loader logic, which is also given to me. Basically, I get all the data within my range. I get the minimum value in each range. I check if it's a threshold, and there's a Boolean value.
Mm-hmm.
And then based off of those Boolean values, this is where all the logic happens. So if the front's clear, it goes forward. If front right or front left is not clear, it moves back slightly and turns to whichever one has a larger scan, which is the other way. And if the front is not clear, it moves back slightly and then turns either right or left, depending on which one has a larger scan.
Mm-hmm.
Finally, again, setting z for distance. Here I am building an instantiated object, has a robot interface to it, and this is your diagnostic stuff. Like, oh, here's where I am.
Mm-hmm.
Here's where I'm driven. Here's what I think I'm looking at.
All right. All right.
Here's me actually calling a loader function, and that's the end.
All right. Very nice presentation, Matthew. Thank you for getting into so much detail about what you did, how you did it. I also like the logic, right? Your explanation of why you did what you did, right? Because that's the most important part, after all, right? If you're going to explain to someone to such a point that they can recreate or at least duplicate what you did, they have to understand why it was done. It's easier in that form. So yep. All right, very well done. Thank you so much. So I sure. So just one sec. Alright everyone, this was Matthew's presentation. Very warm congratulations to him, and I would like to encourage all those of you who would want to try all the courses that we offer certification on to do so, and you can come do your presentation as well, showcase your work, and until next time, keep pushing your ROS